So from this you might have guessed what maximum likelihood estimation is going to be. So the way we are going to use maximum likelihood estimation is that we have already obtained the results D, and using D we are going to get the best estimate, which as of now is going to be called as the MLE estimate for us, because this is the method that we know the best now. Estimate of mu. I told you initially that X is distributed depending on the parameter mu, but we have never gotten a single value of mu. I told you that this is the distribution of X given a parameter mu. So what we are trying to do now is that since we have all of this data, from this data we are trying to get a particular value of mu, which would probably make getting this particular set of data the most likely. So what we want to do is maximize the probability of getting D given mu. So we are going to maximize L of X, and we are going to choose the value of mu that would result in maximum likelihood. As you can see, since L of X is a likelihood function, without going into too much details, you can see that the value of mu that maximizes L of X will also be the value of mu that maximizes logarithm of L of X. So the advantage of working with logarithms is, here you can see that L of X is a product of many parts. So when you actually take logarithm of L of X, you end up with sum of lot of parts. We are going to see how it is going to work now. So I am going to take logarithm of the likelihood function and I am going to maximize it. So this is why it is called the maximum likelihood estimation. Note that the product that we had earlier now has become a sum. This is what we have ended up with, and as we know, this is going to be equal to now how do we maximize the log likelihood function? So this is called the log likelihood function. So one way to maximize it is to take the derivative of the log likelihood with respect to the parameter that we want to choose and then setting it to 0. So we are going to do that now. So we are going to do differentiation of log of likelihood function over the parameter, and we are going to set it to 0. So we can see from here that it is going to be, the xi is going to stay as it is. I'm going to get a 1 over mu here. And this is going to stay as it is, and I'm going to get a 1 over 1 minus mu here. And then I'm going to set it to 0. I'm sorry, there is a correction. When you differentiate log of 1 minus mu, we don't just get 1 over 1 minus mu, but we also have to differentiate this, and we'll get a negative 1. So this is going to be negative 1 times this factor. So instead of this, we're going to have a negative sign here. So continuing with the derivation, after we equate the differential of the log of likelihood to 0, we are going to get xi times 1 minus mu minus, I have just distributed the summation to the two terms, and you know that this 1 minus mu and nu don't interfere with the summation, so we can take them outside. So I'm going to get 1 minus mu times sigma xi minus mu times sigma 1 minus xi, and this is equal to 0. So let us call sigma xi as P. If you recall, you would know that xi would be 1 if I obtained head on ith trial, or it would be 0 if I obtained tail on the ith trial. So sigma xi is nothing but the total number of heads that you have obtained from trial 1 until trial n, and sigma 1 minus xi would be the total number of tails that we obtained in the n trials. So let us call it by n minus p. So the summation becomes 1 minus mu times p minus mu times n minus p equals 0. Simplifying this further, we get mu equals p over n. For the random variable x, which is 1 when we get a head and 0 when we get a tail, is the total number of heads that we have obtained in the n trials over the n trials. It seems very intuitively correct. Just remember this result. We'll be looking at it later on, but this is the flavor of MLE. So in MLE, we use the data that we have already seen to estimate the parameters of the distribution from which we have sampled our variables. Now let us look at one more example, which is the Gaussian distribution.